Assalamu alaikum dear students. Today we shall discuss one of the last chapter of this course, that is applications of derivatives. Derivatives are used in number of disciplines like social sciences, engineering, chemistry, biology, physics. But we will discuss the applications of derivatives in maths, which further are used in other disciplines. Like derivatives are used in finding the rate of change of quantities, to find the equations of tangents and normals at a point, to find the turning points on the graph of functions, to find the approximations. In these we use the derivative. So these are the applications of derivative. Let us discuss these applications by one. So first one is rate of change of quantities. Let y equals to f of x be a function. Here y is dependent variable, x is independent variable, means y depends upon x. Now if we change in x, which implies that x to x plus del x, that this is a change. This means that corresponding change in y is y plus del y. So when we differentiate it, when we subtract these two equations, we simply get del y equals to f of x plus del x minus f of x. So this is simply change in y when we change x. Now when we divide this equation by del x, we simply get del y upon del x is f of x plus del x minus f of x upon del x. So this is the average change in y. Now when we let del x tends to 0 in this equation, we get del y upon del x is dy by dx by definition of derivative, or by the first principle, which is simply denoted by f dash of x. This change, which is represented by dy by dx, this gives us the instantaneous change, or is simply called as the instantaneous change. So this means the change in y with respect to x at a particular point. So simply derivatives can be used to find the changes of y with respect to x at a particular x. Now here dy by dx is a number, so it can be positive, negative, or 0. If it is positive, this is called as the positive change in y with respect to x. That is, y increases when x increases. Similarly, if dy by dx is 0, this means that y remains constant when x increases. Similarly, if dy by dx is less than 0, this means that y decreases when x increases. Now let me consider an example. We have to find the rate of change of the area of a circle per second with respect to its radius when r is 5 centimeter. Let r be the radius of circle with area equals to a equals to pi r square. Then dA by dr gives us the rate of change of area with respect to r, which implies that dA by dr, by differentiating this a, we simply get 2 pi r, because pi is constant. Differentiation of r with respect to r is 2r, that is 2 pi r. Name it equation first. Now we have to find this change at r equals to 5, because derivatives at point gives us the instantaneous changes, which implies that dA by dr at r equals to 5 is 2 pi pi, which is 10 pi. Hence this area changes with respect to r when r is 5 centimeter by 10 pi centimeter square per second. Similarly, you can find the change in the area with respect to r when r is 3 centimeter or when r is 4 centimeter. So simply substituting r equals to 3 and r equals to 4 in equation first. Second example, the volume of the cube is increasing at the rate of 8 centimeter per second. How fast is the surface area increasing when the length of the edge is 12 centimeter? Now let x be the side, means x is the length of the side in centimeter of a cube, v be the volume, s be the surface area. So clearly v equals to x cube, volume centimeter cube. Surface area of this cube is 6 side square, that is 6x square, where x is the function of t. That is, we measure this distance with respect to t, where t is the time. Now this volume changes, rate of change of volume. This means that dv by dt is 8 centimeter per second, or 8 equals to dv by dt equals to dv by dx into dx by dt, where dv by dx is the rate of change of volume with respect to distance, and dx, because x depends upon t position, that is length, depends upon the time. So simply 8 equals to, now dv by dx is 3x square, because here v is x cube, which implies that dv by dx is 3x square. So this means that dx by dt, or dx by dt, is 8 by 3x square. Its unit is centimeter per second. Now surface area is 6x square, while x is the function of t, which implies that ds by dt, because we have to find the rate of change in surface area with respect to time, is ds by dx into dx by dt, because by cancelling or by the chain rule, which implies that it is ds by dx is simply differentiating s, we get it is 12x. dx by dt is by above it 8 by 3x square, so simply 32 upon x centimeter square per second. That is, this surface area changes at the rate of 32 by x centimeter square per second. Now we have to find the rate of change of surface area when x is 12. So this means that substituting x equals to 12, we get 32 by 12, which is 8 by 3 centimeter square per second. This means that the surface area changes by 8 by 3 centimeters square per second when x is 12 centimeter. Similarly, another example, the radius of the circle is increasing uniformly at the rate of 3 centimeter per second. Here rate simply means change with respect to y, in this with respect to distance, with respect to time. Find the rate of change in area. So this means that we have to find dA by dt. Rate of change in area simply means to find dA by dt, that is change with respect to time. Let A be the area, or be the radius of the circle. We know that A equals to pi r square radius, where this r means distance is the function of t, time, that is position depends upon the time, that is this distance is the function of this time, that is r is the function of t. So we have to find dA by dt. Now rate of change of area with respect to time is given by dA by dt. By chain rule, it is dA by dr into dr by dt. But dA by dr is 2 pi r, and this rate of change in the radius is 3, which implies that dr by dt is 3 centimeter per second. Hence, substituting equation, first we simply get dA by dt is 2 pi r into 3. We have to find the rate of change in area when r is 10 centimeter, which implies that dA by dt is 2 pi 10 into 3, which is 60 pi centimeter per second. So this means that the rate of change in area is 60 pi centimeter square per second when r is 10 centimeter. Edge of the variable cone is increasing at the rate of 3 centimeter per second. How fast volume increases when edge is 10 centimeter? Let x centimeter be the length of edge. Its volume is given by v equals to x cube, because side cube is the area of the given volume, given this cube, where x is the function of t, which implies that dv by dx is equal to 3x square. Also, edge means length of the cube, length of the edge of the cube is increasing. Increasing means derivative is positive at the rate of 3 centimeter per second. This means that dx by dt is 3 centimeter per second. So we have to find the change in this volume, that is we have to find the rate of change of volume with respect to time, that is we have to find dv by dt, which is dv upon dx into dx by dt. So substituting dv by dx, that is 3x square, dx by dt, because it is given that the edge of the variable cone is increasing at the rate of 3 centimeter per second. This means that rate of change in the length of edge upon time is
3. So simply we get dv by dt is 9x square. So this is the rate of change in volume, which is 9x square, but we have to find the instantaneous. So simply substituting, we get dv by dt is 9 into 10 square, which is 900 centimeter cube per second. This means that volume of a cube changes at the rate of 900 centimeter cube per second when the edge of the cube is increasing at the rate of 3 centimeter per second, and this change is at when length of edge is 10 centimeter. So thank you.